Hi, in the last video I discussed about a ratio test and I gave you some examples of the ratio test. Okay, so the very last test on the convergence or divergence of the series in this chapter is the root test. So the root test is similar to the ratio test. Okay, let us see the statement of the ratio test. Okay, the series summation n runs from 1 through infinity. A sub n converges absolutely if the limit of n tends to infinity, nth root of absolute value of an is less than 1. Okay, if the nth root of absolute value of an is less than, so you don't need an plus 1 in this series. Okay, if this is less than 1, then it converges absolutely. If the limit of the series, that limit of the nth term, absolute value of nth term, and nth root of that is greater than 1 or infinity, it diverges. And if that is equals to 1, if that limit is equals to 1, it is inconclusive. In that case, you will have to use the different test. Okay, guys, so let us see some examples. So example number 1, again, when does this root test is more helpful to do a problem is if there is a whole power n, whole exponent n, then when you take the nth root, that n will cancel with the nth root. Okay, and then you will have just an left. You will have just the interior thing left. That's why in that case, in such case, if there is a whole power n, then the root test is more applicable. Okay, let us do this example here. So what is the n? So what is an? An is n over 2n plus 1 to the n, right? Now let us take the limit. Limit n tends to infinity. What is the nth root of that? Is n over n 2n plus 1 to the n. See that nth root, this nth root, and then that n exponent cancel out. Okay, so what is left is limit n tends to infinity. All right, and then what is left is n over 2n plus 1. See that when you take the limit, you'll get infinity over infinity, and you use the L'Hopital's rule. The derivative of the top is 1. Okay, derivative of the bottom is 2. This is less than 1. You see that? If that limit is less than 1, the series converges absolutely. So the series converges absolutely. That's what you got. Okay, so question number 2, example number 2. I think this example is question number 43 from the book. Okay, so question number 43 from the book, it has negative 1 to the n over natural log of n to the n. Okay, so here what is an? So an here is negative 1 to the n over natural log of n to the n. Right, now let us take the limit again the same way. Okay, limit, I'm using the root test. Okay, n tends to infinity, nth root of that thing, negative 1 to the n. Oh, by the way, absolute value, you will need the absolute value as well, but you know that in this case, since everything is positive, you don't need the absolute value. Okay, so the absolute value of, and then natural log of n to the n. Okay, what do you get? Absolute value of negative 1 to the n is just 1. So over, this is what you will get, limit n tends to infinity, right? And then you get 1 over natural log of n. When n tends to infinity, what happens? This goes to 0, right? Which is less than 1. 0 is less than 1. So the series converges. The series converges absolutely. That's what you get. Okay, guys, so the next example I want to do is example number 3. I think this is question number 47 from the book. Okay, so what is an here? So an is n over 3 to the n, right? So let's take the limit as we did before. Limit n tends to infinity, nth root of n over 3 to the n. What do you get? You get limit n tends to infinity, n to the 1/2 over 3 to the just 3, right? N to the 1/2. So not 1/2, 1 over n, not 1/2, 1 over n. Okay, n to the 1 over n. Okay, So now how much is that? So what is n to the n? So basically you can write this as 1/3 and then limit, and then n tends to infinity, n to the 1 over n. Do you remember that in the chapter, the L'Hopital's rule, how did we find the limit of x to the 1 over x? You took the log and then find the limit, use the L'Hopital's rule. Do you remember that? We did that way. In that case, what did we do is we said y equals to x to the 1 over x, and then natural log of y is equals to, you did 1 over x natural log of x, right? And then you take the limit. When you take the limit, what do you get there? You take natural log of y equals to limit x tends to infinity, natural log of x over x. So this is infinity over infinity. Use the L'Hopital's rule, 1 over x divided by what? 1, right? And when you take x tends to infinity, you get 0. So natural log of y is 0. So y is e to the 0, that is 1, right? So limit of y is equals to 1. So that's what we get, okay? So I am using exactly the same technique here. So you get, when you take 1 over 3, this will becomes 1, which is 1 over 3. Is this less than 1? Yes. So the series converges. So converges absolutely by root test, right? Absolutely by root test. That's what you got. Okay, so all of these are by root test, and then by root test. Okay, root test. Okay, let us do another example. Example number 4, which is a summation n runs from summation n runs from 2 through infinity, n over natural log of n. So it is n over natural log of n and then to the n, right? So what is an here? So an is equals to excuse me, n over natural log of n to the n, right? Let's take the limit then. Limit of n tends to infinity, nth root of that thing, n over natural log of n to the n. What do you get? And the absolute value also, right? Since everything is positive, so you don't need the absolute value there. Limit n tends to infinity, right? You can write n to the 1 over n divided by natural log of n. You see that? So when n tends to infinity, what happens? The top becomes 1, as we did before, right? As we did here. The top becomes 1 and the bottom becomes infinity. That is basically 0, which is less than 1, right? Which is less than 1. So hence, what do you get? Hence by root test, the series converges absolutely. Okay, that's what you do. Okay, so from for example 5 and 6, you can use any test that you know. All right, that's what we want to do here. So use any test to check the convergence or divergence of this series. Okay, so how do I do this one then? So which series do you think I can use here? Because basically this can be simplified as like summation n runs from 1 through infinity, -1 to the n times this is like, you can write 3/2 to the n times 3 to the -2, right? Because you get 3, this one can be written as 3 to the n minus 2 can be written as 3 to the n times 3 to the -2, right? So if you do that, you can write 3 to the -2 is 1/9, right? Because it will move to the denominator and then it will be 1 over 3 squared. And then you can write this whole thing n equals to 1 through infinity. You can write basically -3/2 to the n. Oh, this is geometric series with common ratio less than -1, okay? So which is absolute value is greater than 1. So it is a geometric series. And again, this problem can be done in different ways too. You can use maybe alternating series test, or maybe the ratio test you can try, okay? So you can try different tests, and that may give you the right answer too. So I like this geometric series test. It's just straightforward. Geometric series with value of r equals negative 3/2, right? With absolute value of r is negative 3. That means, sorry, r is negative 3/2. Absolute value of r is positive 3/2. Okay, that is 3/2, which is greater than 1. So the series diverges. The series diverges. That's what we got. Okay, so let us do another example. This example is question number 65 from the book. Okay, let us do that question number 65 from the book. So we have, let us say, a sub n. I mean, again, you can use any test you want. Okay, so here an equals to n factorial over n times, you don't need a parenthesis there, n times 7 to the n. What will be an plus 1? Let's see that. So if you do that, because there is no whole power n, so I'm not using the root test. Root test is useful if there is like whole power n, whole power n, and whole power n kind of thing. Okay, so what is an plus 1? Is n plus 1 factorial divided by n plus 1 excuse me, times 7 to the n plus 1. Now let us use the ratio test. Limit n tends to infinity, absolute value of an plus 1 over an equals to what? Limit n tends to infinity. Let us plug in those values. Okay, so what do you get? So you get n plus 1 factorial divided by n plus 1 times 7 to the n plus 1 times, so an should be divided, but I write the reciprocal of the product of the reciprocal. So I'm doing n times 7 to the n divided by n factorial. Okay guys, so how do I do this is, let us simplify. Limit n tends to infinity. Okay, and then you can write n plus 1 times n factorial divided by n plus 1 times, you can write 7 to the n times 7, that is 7 to the n plus 1 times n times 7 to the n over n factorial. Let us cancel n factorial and n factorial, n plus 1 and n plus 1, 7 to the n and 7 to the n. So what do you get? Basically you get, basically you get n over 7, right? Did you get n over 7 here? So basically you get n over 7, right? So that is basically, let me see, n factorial 7n. Okay, I think it's good. So an plus 1 over an. Okay, so that will be, what I can get there is n over 7, and then there is a limit n tends to infinity. So when limit n tends to infinity, this become infinity, right? So by the ratio test, the series diverges. This is what we got. Okay, so this is how we use ratio test and root test. But now you may be curious. So we learned so many tests, right? We learned so many tests, like 7 or 8 tests. But which test should I use? How do I start the problem? Okay, that you may be curious on that. And again, some of the problem, when you look at the problem, and then you can just right away you can find out like which test may be easier. Okay, so usually we start with the you see if the nth term goes to 0 or not. If nth term does not go to 0, the series diverges, right? And then look at if the series follow any special type of series. For example, if it is geometric series, then we know what is the result for the geometric series. If the common ratio is less than 1, converge. If the common ratio, absolute value of the common ratio is greater than 1, then it diverges. Now also look at if it's if it has like p series type of, say 1 over n to the p. If p is greater than 1, it converges, and if p is less than 1, it diverges. And if there is a alternating series or telescoping series type of series or not. Okay, and after that, then you can see, can I use the integral test or the root test or the ratio test, like that? Okay, or can I compare the given series with a series that has a known convergence? Okay, you can you write like, for example, if there is sine n over n square, then you can write that is less or equals to 1 over n square, because the sin n is less than n, right? Series of 1 over n square, but the series of 1 over n square converges by the p series test, right? So in that case you can use the p series and then say that the bigger series converges to the smaller series converges, and so on. Okay, so these are the techniques to test the convergence and divergence of the series. This is the end of section 9.6. Next we will be talking about a new section, that is a Taylor's polynomial and its approximation. Okay guys, all right, thank you.